right, this is a video over section 1.1, linear equations and graphs. We're going to be looking at a few different topics. These are all prerequisite material for Math 135. So things that either you were expected to see in a high school level class that you had taken previously to coming to Ivy Tech, or if you took Math 043 or tested into Math 135. So starting with equality properties, we're looking at what is an equivalent equation. An equivalent equation is when you have two equations and they have the same set of solutions. So when we look at solving an equation, what we do is we try to isolate our variable, and that is done by making equivalent equations to the original. So things that we can do to create an equivalent equation: we can add or subtract the same quantity from each side of a given equation, so we keep it balanced as long as we add the same amount to both sides or subtract the same amount. Each side of the equation can be multiplied or divided by the same non-zero quantity. You can't do multiplication or division by zero. You would clear out your whole equation or make it undefined. So anything that is non-zero, we can multiply and divide both sides by. So to solve a linear equation, we will perform these operations on the equation to obtain simpler equivalent forms until we obtain an equation with an obvious solution. So we're going to go through these. There's a couple examples here. This first one, we have 8x minus 3 times the quantity x minus 4 equals 3 times the quantity x minus 4 plus 6. So one of the first steps that I like to do before I do anything with moving, adding or subtracting or multiplying or dividing anything to both sides is I always check for, is there anything I can simplify on the left side? Or is there anything I can simplify on the right side? So it looks like we have the distributive property here. So if we want to distribute this -3 to everything inside this parentheses, and then this 3 in the second side on the right side to everything inside that parentheses. So we're going to rewrite this equation as 8x minus 3x plus 12, because we get a -3 times a -4, equals 3x minus 12 plus 6. Okay, before I start isolating x, I can notice that there are two like terms on the left. There's two terms that both have x to the first, and there's two constant or like constant terms on the right side, so they're just numbers. So we can combine like terms before we try and solve. So 8x minus 3x would be 5x plus 12 equals, and then we have our 3x on this side, and then -12 plus 6 is -6. Now we're at the point where we've simplified everything we can on the left and everything we can on the right. Now we want to get x by itself. So we're isolating x to try and solve the equation. So one thing we can do is we can move the 3x to the other side. To move an entire term from one side to the other, we do opposite operations of addition or subtraction, depending on what the sign of this coefficient is. So since this is a +3 connected to that x, we're going to subtract 3x from both sides. Now, I like to do this in different colors to show my work. I don't always like putting it right underneath because that's kind of not a true statement. We want to keep everything in line with our equation. So notice everything in blue is the original equation, and what I'm doing to both sides, I have in red. So I'm subtracting that 3x from both sides. What we'll see is that on the right side, that's going to cancel out to a 0 for that part, but we will combine these on the left side and get 2x plus 12 equals -6. Similarly, we're going to need to move the 12 away from the 2x because we're trying to isolate for x and solve for that variable. So I'm going to subtract 12 from both sides, and you'll see me doing that here. And I won't do this for every problem. A lot of times once you've got the hang of moving terms around, a lot of people just do it in their head. I do recommend writing your steps, but sometimes depending on your instructor, you may not have to write every single detail out. It just depends on what they want. We're going to get 2x on the left because the 12 and -12 cancel to a 0. And then -6 minus 12 is -18. We'll divide both sides by 2 to get the x by itself, because right now, when you're disconnecting a number from an x, that means they're side by side like that. That is multiplication. So the opposite operation of that is division. So if I divide both sides by 2, I get that x equals -9. So there is my solution. Now I can perform a check if I want to show that this is correct. I will do it on this first equation and maybe one of the other ones. I won't always do the check. I'll leave that to you. But we have 8, and we're going to plug it in for all the x's. So 8 times -9 minus a 3 times -9 minus 4 in that parentheses equals 3 times -9 minus 4 plus 6. Okay, so if we want to check that, 8 times -9 is -72. This is order of operations, so I need to add the -9 and -4 together first because they're both negative. So that's -13. Same thing on this side, so I'll still have a multiplication step after this on both of those. And then we have our plus 6. -3 times a -13 is going to give us a positive 39. So we're going to have -72 plus 39 equals, this time we have a positive times a negative, so that's going to be -39 plus 6. If we combine our like terms on each side, we have that 72 negative 72 plus the 39 is going to be a -33. And -39 plus 6 is also -33. So that checks out because our left side and our right side match. So you can perform a check anytime you solve an equation to see that it is an actual solution. Okay, let's look at my second example here. We're going to solve this equation and note that we do have some things we can simplify first. I can distribute this -2 on the left side. We're going to talk about what to do with the fraction in just a minute. So I'm going to distribute first. This is going to be 3 minus 2x, -6, because we're going to get -2 times 3. We'll have an x over 3 on the right side minus 5 still. We can't combine those together because they do not both have x, so they're not like terms. On the left side, we have a 3 and a -6 that are both constants. So if we add those together, we get -3. Now, you have a couple choices right here once you get to this point. You could try and solve it with the fraction on that x intact. You can write that out front as like 1/3 x. The only issue with that is when you go to move your x's over to be together, you will have to get common denominators because to add and subtract fractions, you have to have common denominator. A method we use a lot of times in our algebra courses is we teach students to multiply through by the LCD. That's the least common denominator. So since we only have the one denominator that we see here, our LCD is that value. So if we multiply both sides by 3, we'll have to do a distributive property to distribute that. What we'll see though is it'll cancel out the fraction in that first term on the right side. So we're going to get -6x minus 9 equals, that'd be 3x over 3. So that's just going to be x and then -15. Okay. So then I would subtract my x over. So I'm going to have -6 minus 1x. So that's going to be -7x. And I'm going to do my other step here together too, since we kind of already showed the full step work up above. If I do -15s on this side, and I'm going to move the -9 over because we need to move it to the right side, I'm going to add the 9. So -15 plus 9 is going to be -6. Divide both sides by the -7 to get the x by itself. And negative over negative is a positive. So this one will have an answer of 6/7. And that is a reduced fraction. There's nothing that goes into both 6 and 7 evenly. There's no similar common factor. All right, let's look at another one. So this one's a little different. It has 2 different denominators. So if I want to clear out my fractions and make things a little easier to solve, I can do that as long as I multiply both sides of the equation by the same thing. So the LCD for this group would be 6 because 2 and 3 both go into 6. That is the smallest number they both go into. So I'm going to multiply this side by 6, which means I also have to multiply the right side by 6. I like to go ahead and write this as a distributive property without doing the math yet. So I'm just writing 6 times the first term minus 6 times the second term. And the reason I like to do it that way is because it's easier to see the cancellation of these factors, because 6 does not completely go away because 2 only goes into 6 a certain number of times. So when we reduce this, we're going to get a 3 that we need to distribute to everything on top. And then when we reduce this one, we're going to have a 2 that we need to distribute. So this is going to be 3x plus 6. And then this is a minus 2x because we have that minus sign we need to not forget about, equals 30. Okay. Combine the like terms on the left side. We're just going to get 1x plus 6 equals 30. subtract over the 6, and we'll get 24. So we can double check to make sure this one works. So I'm going to do another one where I show a check. This is 24 plus 2 over 2 minus 24 over 3 equals 5, plugging it back into the original equation. That would be 26 over 2 minus 24 over 3 equals 5. So that is 13 minus 8, which does equal 5. So it does check out. So you can always do those checks, remember I said, to make sure you've got the correct solution. All right, let's look at this next one. It says, this is x plus 1 over 4 equals x over 2 plus 5. This time my LCD is actually 4 because 2 goes into 4 evenly. So we don't have to use, sometimes students will use 8 here. That's a little bigger than you need. So I'm going to multiply this side by 4 and this side by 4 of my equation, both sides. So we're going to distribute as needed on that right side. So 4 times the x over 2 plus 4 times the 5. On the left side, the 4s are going to completely cancel and just leave me with the numerator, which is x plus 1. Here, though, we'll reduce and get 2 times x, which is 2x, and then 4 times 5 is 20. I would probably subtract the 1x over onto and move it to the right side, just because I like to keep my x's positive if I can. So that would just be a 1x. And then I would subtract 20 over to the left side. So that's going to be 1 minus 20, which is negative 19. So there's my solution for that one. Now, something else we can do. The above examples were what we said are linear equations, but they were all in one variable. So a variable that we were using was x. In general, a linear equation, which is a first degree equation. So whatever our variable is, it's to the first power. Is in if it's in one variable, we can write it in the standard form for a linear equation in one variable. So notice it's your coefficient times your x plus your constant equal to 0. So we already solved this one up above in one of our examples. We had that it was 6/7, but before we got to that stage, we were at this. So I'm just going to write a little note. You can go back up and review the solving steps for this one. But before we actually divided by -7 and got the solution, we had this step. It was negative x equals -6. To get that in standard form, instead of solving it for x, you move everything to the left side and get it set equal to 0. So we'll have -7x is already on the left side. We'll add the 6 over and set it equal to the 0 because we're just adding 6 to both sides. So that would be the standard form for that specific one. And notice that a cannot equal 0 in standard form, because if it does, you wouldn't even have your x to the first power. So you wouldn't have a linear first degree equation. Okay. So our next topic is going to be looking at solving a formula for a particular variable. So this is just taking a formula that's been presented to us and rearranging it so that a singular variable is all by itself on one side. All of the other variables and numbers are all going to be on the, usually I have the variable I'm solving for on the left, and then everything else is on the right. We're going to do an easy one first, and then we'll do one that has a little bit more complexity. So if you deposit a principal P in an account that earns simple interest at an annual rate R, then the amount A in the account after T years is given by A equals P plus PRT. So this is a financial example. So notice that you have to read your directions to see what they want you to solve for. They want us to solve for R, and notice they say in terms of A, P, and T. So A, P, and T are the variables that are allowed to be on the other side of the equation. So I like to start by rewriting my equation that they gave me. And I like to underline any of the terms that have my variable that I'm trying to isolate. So there's only the one term here. It's this P times R times T. So that's why I said this one's a more simplistic one to solve. So we just want to isolate this term first. So we're going to subtract this P over to the other side. Since it doesn't have a sign, we're assuming that the coefficient there is positive. So we'll have A minus capital P equals the PRT. P times R times T are all connected by time since we don't see anything in between those variables. So to get rid of those from this side, we're going to divide by PT. You can do that because you're dividing by kind of like two factors, if you think about it that way. So if this was a 2 and this was a 5, we're really dividing by 10, okay? Because we're dividing by them both at the same time. All right, so I like to rewrite that with, like I said, I usually put my singular variable on the left and then what it equals on the right. Just kind of a standard protocol. You can write it the other way. This is just typically how we write it in algebra. All right, let's look at one that, like I said, has a little bit more complexity. It says if a cardboard box has a length L and a width W and a height H, surface area, which is the area of all the surfaces of that solid. So like if you think about like a box or a package that you get, you could imagine cutting up all the different rectangles. There'd be 6 of them if it's a rectangular box, and measuring the area of each one and then adding all those together. Some of those are going to have the same area, like the top and bottom of the box are going to match. So that's where they come up with the formula here. So surface area equals 2 of the length times width, plus 2 times the length of the heights, times the heights, and then plus 2 times the heights times the width. So that's those different pairs of those sides of the boxes, okay? We're going to take that formula and solve it for H. So the other side's just going to have the variables S, L, and W. Note, and they can also have coefficients, that's fine, but you can't have an H on the other side. H has to be a single H all by itself on one side of the equation. Why I said that's important is because you'll notice in this equation, there are 2 H's. There's one in the second term on the right side, and one in the third term on the right side. So I'm going to underline both of those. So we want to isolate both of these on one side. So when you have multiple of the variable that you're trying to solve for, you want to get all of those H containing terms on one side, and any terms that do not have H, we want to move to the other side. So we're going to subtract over that 2LW. So S minus the 2LW equals 2LH plus 2HW. Now, once you have all of your H terms on one side together, you can factor it out as a greatest common factor. So it's like reverse distributing. So we're going to pull the H out. You're really pulling it out by division. You're dividing it out of each term. So that leaves me with a 2L plus a 2W. By doing that, we've now got a single H showing up in our equation because we pulled it out as a greatest common factor. That allows us to solve for it all by itself. So we're going to divide over that parentheses. So H is going to equal the S minus the 2LW on top that we had on that side over there, divided by the 2L plus the 2W. Okay. All right, so we're going to switch gears for a little bit now, and instead of talking about just equations, we're going to be talking about inequalities. Inequalities, remember, have things like less than, greater than, less than or equal to, greater than or equal to. So for real numbers A and B, A is less than B if there exists a positive number P such that A plus P will make it equal B. A less than B is equivalent to B is greater than A. Notice that they swapped which one was on each side, but they made sure the opening, remember this, when I was in grade school, we of course said the alligator, the shark, whatever you want to call it, but the greater than part is still opening to the B. They have to reverse. So if you swap the sides of your inequality, you have to change the direction of the inequality to make sure it's still pointing or opening to the correct variable or expression, okay? So an equivalent inequality will result, and the sense of the direction will remain the same if each side of the original inequality has the same number added or subtracted to it, or is multiplied or divided by the same positive number. So what that means is when we were solving equations, we could add or subtract something to both sides. We could multiply or divide by any non-zero number we wanted to on both sides. With inequalities, you can add or subtract anything from both sides. That doesn't change. But when you multiply or divide, to keep your inequality to have the same direction, in other words, it's opening and pointing the same way, that only will stay the same if you multiply or divide by a positive number. If you multiply or divide by a negative number, you're going to have to reverse the direction of your inequality. So let me just see if I can make that make sense to you. If you have a statement that is true, let's say 2 is less than 4. That is true. If I multiply both sides of that inequality by -1, we're just going to multiply both sides by -1. Notice that if I do this, it's not going to be true anymore because we're going to get something that's false if I don't change that direction. So -2 is not less than -4. In fact, -4 is smaller on the number line. So that's why when you multiply or divide by a negative number, you have to change the direction to make sure that you get the correct answer. So -2 is greater than -4, okay? It's just something to be aware of. So we're going to put that into practice right away with this first example. So it says solve the inequality. We have x over -6 is greater than 4/5. So to get x by itself, they're dividing by -6. So I need to multiply both sides of my inequality by a -6. On this side, since there's a fraction, you might want to write that as -6 times over 1 because it makes the multiplication easier. But because I'm multiplying by a negative, note that I'm going to, when I write this down on the next line, I'm going to change the direction of my inequality. That's because I'm multiplying by a negative on both sides. So this is just going to be x, and then this will be -24/5. So x is less than -24/5. Okay. Some things to note about what we might have to do when we write our answers into our homework or for our test. We a lot of times like to write our answer in interval notation, which is a way to describe the solution set, because it's actually an infinite number of solutions. Because even if it's between A and B on a number line, there's an infinite number of numbers between A and B because you've got all those decimals and fractions, not just the integers. Okay. So when we look at this, this is always from least to greatest. So left to right when you look at the graph. And we use a bracket if we include the endpoint. That means we have the equal to. And we use a parentheses if we do not include the endpoint. So notice just less than or a greater than. You do not use a bracket there. Also, infinity is a concept, not an actual value. So we do not, it goes on forever. So we use a parenthesis, an open ending on that. So let's read kind of our information over here. So these are different ways you can write in between inequalities. Notice the equal to, you get brackets. Notice the non-equal to, if you don't have that, you get a parentheses. So we have the interval notation, what we get when we solve the actual inequality, and then what does that look like on a graph. In the table, the numbers A and B with A less than B are called the endpoints of the interval. It's a closed interval if it contains the endpoints. That's the brackets. It's an open interval if it does not contain its endpoints. And that can be on either side. So it can be, half open, half closed. Parentheses are used to indicate that an endpoint is not included. Parentheses are always used for the infinity. So just summarizing what I said. So let's go ahead and solve this inequality. We're going to write the answer in interval notation and then sketch a graph of the solution. So the first thing I note on this one, I'm going to rewrite it, is that I'm going to have some distributive property to take care of right away. So we can solve for x. And pretty much we solve the same way we solved equations unless we encounter dividing or multiplying by a negative. That's when we have to worry about the direction of our inequality. So this is going to be 4x plus 6 is less than 6x minus 12 plus the 10 comes down. We have some like terms on the right side that we can go ahead and combine. 4x plus 6 less than 6x minus 2 because we combine the negative 12 and 10. I typically like to move everything to the left side when I do inequalities, even if it makes the answer negative on that x part, just because that's easier to read. Because when you read from left to right, if you see the point first, you read that as less than. If you see the opening first, when you read from left to right, you read that as a greater than. So I'm going to subtract the 6x over just because I like to have my x on the left side. So that's going to be -2x. We have our less than symbol. Notice I'm not changing the direction here because I was adding or subtracting something from both sides. You don't do anything to your inequality direction when you're adding or subtracting. When we do this one, we need to subtract the 6 over. So that's going to be a -8. Okay. And then now I need to divide. So I'm going to emphasize that I'm dividing by a negative here by showing a different color. Dividing by a negative. Okay. When that happens, that's why my direction is going to change. So x is now going to be greater than a +4. Now, if I graph that, because sometimes it's easier to get the interval notation from the graph. We would have 0, 1, 2, 3, 4, 5, and so on. So when we do, now some people might have learned like open circle or closed circle in a previous class, but when we do this for interval notation, we like to use the parentheses in the bracket. We do not have an equal to symbol, so we're going to be using a parentheses. The parentheses should open the direction that we're going to shade. So notice this is greater than, so we're going to be going to the right of our number 4. So we're going to shade everything to the right. So that goes on forever. Okay. So this would be interval notation of 4, because we read it from least to greatest with a parentheses to infinity, which is the positive infinity is where we're headed. And remember, we always use a parentheses on infinity. So there's my interval notation and my sketch. All right, let's talk about the next one. On the types that we see here, we're going to be looking at, this is what we call a compound, or I like to call it a string inequality because it's connected. You have 2 different inequality symbols. You could split these up and try and solve it, but then you have to interpret that as an and statement, which I think is more complicated. So you kind of have a left side, a center side, and a right side. As long as we're isolating the x in the middle, whatever we do to the middle, we do it to both the left and the right as well. You can solve that kind of all at the same time. So I'm going to subtract 3 from all 3 sides. Okay, so that's going to be a -6 less than, because I'm trying to get the x by itself. I'll have a 2x. I'll have this being 0 now because I'm subtracting 3 from the center. And then 9 minus 3 is going to be a 6. So I have -6 less than 2x less than or equal to 6. Then I can divide all 3 sides by 2. Notice I'm not dividing by a negative, so I didn't change colors and emphasize that because I'm not going to be changing the direction of any of my inequalities. So this is -3 less than x less than or equal to 3. If I sketch that, this is going to be one where we're shading in between 2 values because our x is in the middle. So let's say we have -4, -3, -2, -1, 0, 1, 2, 3, and 4. Now, the -3 is got no equal to next to it, so it's going to be a parentheses, and I'm going to be shading in the center because x is in between these 2. 3 is got the equal to, so I'm going to put a bracket, and we're going to shade everything in between. Now, this is really easy to read as interval notation from least to greatest. This is all values from -3, but not including it, up to +3, and we do include 3. Okay, so there's my interval notation. All right. We're going to now focus for a little bit on solving word problems. So some things to think about when you're solving a word problem. You want to read the problem carefully and introduce a variable. You'll usually write out let x be such and such. That will represent your unknown quantity that you're looking for. Often the question in the problem will indicate the appropriate choice for the variable. They might tell you exactly what to use for x or y, once we get into 2 variables. But if they don't, you can write it out yourself, okay? Identify other quantities in the problem, known or unknown. Express those unknown quantities in terms of the variable you introduced in step 1. So this is if we'll have like a multiple part thing, where maybe we use the x not just for one piece, but maybe multiple pieces. Or we have 2 different variables, but we're not really wanting to introduce a y yet because we don't know how to handle it. So maybe we can write the second unknown in terms of our x. We'll write a verbal statement using the conditions stated in the problem, and then write an equivalent mathematical statement, which could be an equation or an inequality depending on what they were asking. Solve it and answer the question posed in the problem. Check the solution in the original problem. Make sure it makes sense in the context of what we're doing. So let's look at this first one. It says Alex purchases a big screen TV, pays 7% state sales tax, and is charged $65 for delivery. If Alex's total cost is $1,668.93, what was the purchase price of the TV? So right there, that question at the end is what we're looking for. So I'm going to say, let's let X equal the purchase price of our TV. Okay. I have a couple other things going on. I do know the delivery price. I don't need to define that, but I don't know what the sales tax is going to be. I know it's going to be 7%. It's going to be 7% of what he purchased. So we're going to write that as in terms of X. So when you do a percentage of something, you do that decimal version of the percent. So you move it 2 places to the left, or you can divide by 100 to turn it into a decimal. So it's 0.07 times X. This is going to be the sales tax amount. Okay. Then we kind of want to think about how does a purchase happen? Well, when you get a total price or a total cost, you had your purchase price
plus any sales tax. It's added on to the cost, plus any delivery. And that equals the total cost. So we can now write our equation. Purchase price, I don't know. Sales tax will be 7% of that, so 0.07 times X. Delivery is a fixed amount of $65 in this problem. Total cost we knew was $1,668.93. We can combine our like terms. This is a 1 and this is a 0.07. So if we add those together, we get 1.07x plus the 65 equals 1,668.93. Next, I would subtract over the $65. So 1.07x equals, I got $1,603.93 for subtracting it from that big amount. We're going to divide by 1.07 to get x by itself. And that comes out to a nice number when we do that. It's going to be $14.99. Now, that is our purchase price of our TV. So usually in a problem, we will put units on that, and that would be dollars. So you make sure this makes sense in the context of the problem. So we could go back in and plug it in and make sure it makes sense. So if I went to a store and I had $14.99 as the purchase price, I times that 0.07. So I'm doing this on a calculator off to the side. That'd be $104.93. You add that to the purchase price. That gives you $1,603.93. That's what we had right before we did our division step. We add on the $65 for delivery. We get the $1,668.93. So this does work out in the original setup. And it makes sense that if you're paying this much for everything, tax is not going to be huge. It's going to be based as a percentage of the price. Delivery is not huge either here. So it makes sense that the TV price is pretty expensive. Okay. Now let's look at this next one. It says a golf course charges $52 for a round of golf using a set of their clubs and $44 if you have your own clubs. So you get charged no matter what, but if you rent their clubs, you're going to pay an extra $8 essentially. If you buy a set of clubs, so you're tired of renting for $270, how many rounds must you play to recover the cost of the clubs? So we're going to do two things. First of all, we're going to say let X equal the number of rounds, because that's of golf. That's what they asked us, how many rounds. So we're going to have a side, so we're recouping. So recovering the cost of the clubs means that our amount spent renting equals the amount we spend with our own clubs. Okay, we're kind of breaking even on that. So if you don't ever buy your own clubs, you're going to always pay $52 for every round of golf that you play. If you do buy your own clubs, you're going to pay $44 for every round of golf that you play. So that's 44x. But you have to also include that you've spent $270 to obtain your own set of golf clubs. So we're kind of trying to figure out how many rounds of golf did they need to play to where now they're making out with a better deal. So at this point, from this point on, every time they go play golf after this, they're going to be saving money because they've kind of recouped that cost. So we're going to subtract the 44x over, and that is going to give us 8x equals 270. We'll divide both sides by 8. Now this one comes out to a decimal. And a lot of times you just have to read the directions in your homework or on your quiz or defer to your instructor because they may want you to leave it in a decimal form, or they may say, that doesn't make sense in the context of the problem because you can't play a part of a round of golf. So we would usually round this depending on, the rules of the problem. So I'm going to round this up since it's a 0.7 to 34 rounds of golf. After that point, any new rounds of golf that they play, they're going to be saving that $8 every time. Okay. But they do have to recoup the cost of what they spent on the golf clubs. All right, and then the last part of section 1.1 is profit loss analysis. So profit P, that's what we use for profit, is equal to revenue minus cost. So revenue is always the R, capital R, cost is the capital C. So this is kind of a business model thing. If you want to know how much profit you're going to make at your own business, you have to say, well, how much did I sell everything for? What money did I make when I sold stuff? Minus, did I have to buy equipment? Did I have to have someone manufacture it? So what were my costs tied into my problem? So when P is less than 0, so if you do revenue minus cost and you have a negative, then your company is losing money. Your costs are exceeding your revenue. They're so much larger than your revenue that when you subtract, you get a negative. If P equals 0, then your company has broken even. So your cost equals your revenue. That's going to be an important one because they sometimes ask us to solve for breaking even. So I'm underlining that because we will use this one a lot. When your profit is greater than 0, so you get, R minus C comes out positive, the company is making a profit, so your revenue is exceeding your cost. Oftentimes it'll be helpful to talk about when a company, like I said, breaks even. And that is when we set cost equal to revenue, because we're saying if they were subtracted, we get a 0. So a university club plans to raise money by selling custom printed t-shirts. They find that a printer charges $400 for creating the artwork. So they've got to get the artwork created first. And then the person that's printing it also is going to charge them $3.50 per shirt that they print. Then they're going to turn around and go to their university and they're going to sell the shirts for $15 each. How many shirts must they make and sell to break even? So X is going to be the number of shirts. Okay. Our revenue is usually an easier equation. That's what they're selling it for. So that's $15 for every shirt. The cost is going to be what they had to do to get it made. So they had to pay $400 up front just to get an artwork design. Plus every shirt that they create, they're going to charge, the printer is going to charge them $3.50 per shirt. So notice that per shirt, that's why we have the X there. So when we break even, we set our revenue equal to our costs. And that's because when you break even, that's when P is equal to 0. So if you look up here, if P is 0, you would add C over and you get revenue and cost are equal. Okay. So we're going to write this out. This is 15x equals 400 plus 3.50x. I would subtract the 350x over to the left side. That's going to be 1150x equals 400. Divide both sides by 1150. And again, this is one I believe that comes out to a decimal, so you will defer to your directions, but we're going to round to the nearest integer on this. So I'm getting 34.7826 and it keeps going forever. So I'm going to write out a little bit of that. It's approximately 34.7826 ... So if we're rounding to the nearest integer, this would mean that they need to break even, they would need to make and sell 35 shirts. Notice I'm putting my units because of the context of the problem. All right. Then we have an all-day parking meter is taking only dimes and quarters. If it contains 100 coins with a total value of $14.50, how many of each type are in the meter? So we have 2 types of coins. So we're looking for 2 different answers here. So X, we're going to let be the amount of dimes, just because that's the first one they told me. And we have 100 coins. So we don't really want to call the quarters Y because we don't really know how to handle that yet in our class. But we can write that we had 100 coins minus the number of dimes, because you only have dimes and quarters. That's going to be the amount of quarters. So if I have 50 dimes, I'm going to have 50 quarters. If I have 10 dimes, I'm going to have 90 quarters, okay? Because it has to add up to that 100 coins. And then the total value is $14.50. So this is where we have to know the value of a dime, which is 10 cents, the value of a quarter, which is 25 cents. So these are our values. To get the total value, we're going to have to multiply every dime by 10 cents. So if I have 6 dimes, it'd be 6 times 0.10, and all the quarters times 0.25. That'll give us the money amount. So we're going to have the 0.10 times the X plus the 0.25 times the 100 minus X equals the total value that they found inside that, which was $14.50. Okay, so we have 0.10x. We're going to distribute the 0.25, so that's going to be 25, because 0.25 times 100 is 25. And then we have minus 0.25x once we distribute that. equals the 1450. Combine our like terms on the left, that's gonna be negative 0.15x. I'm gonna go ahead and subtract the 25 over. That's gonna give me negative 10.5 on the right side. And then we divide by the negative 0.15. So we're trying to get x by itself. Now you have a negative over negative, which is good because if we didn't, this wouldn't make sense in the context. That's gonna come out positive. We shouldn't have negative numbers of coins. And that gives me 70 for x. Now, x was the number of dimes. That means we're gonna have 70 dimes in that parking meter. And then 100 minus 70 means that I'm gonna have 30 quarters. So this is the breakdown in that specific parking meter. All right, and then the last one from section 1.1. A rock concert brought in $432,500 on the sale of 9,500 tickets. If the tickets were sold for $35 and $55 each, how many of each type did we sell? So we didn't really give you what kind of tickets they are. So I'm going to do type A and type B. So X is going to be the number of A tickets because we don't really know anything else about them. And then we don't have, I don't want to use Y for B tickets, but I do know that there's 9,500 tickets. So 9,500 total tickets minus however many type A's we have would be the number of the type B tickets. And then we have our money amounts, right? They said that we're just gonna go in the order they gave it to us because that's how they usually set these up. So $35 for type A tickets, so that's 35x. Plus it's $55 for all the type B tickets, which is a combination expression right here. We're gonna have to put that in there as parentheses. 9,500 minus X. That's what I call the leftovers. If this is 1,000, this is gonna be 8,500, okay? And then we set that equal to the total amount of money that they made, which was 432,500. Okay, we're gonna distribute the 55 to both of those parts. So 35x plus that would be 522,500 for that first part, minus 55x equals 432,500. Combine like terms on the left, that's a negative 20x. I can also subtract the 522,500 over to the right side. That's going to give me negative 90,000. And they're both negative, so when I divide, I'm going to get a positive. That's going to come out to 4,500. So we're going to have 4,500 of the type A tickets. I just called it type A since they didn't give me any way to distinguish it. And then this is 9,500 minus that. That's going to be 5,000. So we're going to have 5,000 of the type B tickets. All right, that is the end of the video for section 1.1.